Collinearity is usually a quick evaluation, but there's a lot that goes into it. It's often presented as something that is, quote, either a problem or, quote, not a problem. Screen for it, and then move on if you don't see a major issue. And there are obvious cases where collinearity alarm bells go off when one variable is literally a linear combination of the other or something close to it. Usually that's something structural in the way your variables were collected and or measured, and a mistake you may have made by including two variables that kind of measure the same thing. But relationships between your predictors exist on a continuum. There are situations like this one, where we don't have strong evidence of collinearity, and yet the relationships between predictors can cause problems for the analysis. These problems aren't insurmountable, but they should be considered carefully. Let's look a little more closely. One way to examine how much of the variance in one predictor can be explained by the others is the variance inflation factor, or VIF. What happens behind the scenes is that a regression model is developed with one predictor as the outcome and the other predictors as the predictors. 1 over 1 minus r squared for that model is the variance inflation factor. And it's an estimate of how much variance of that predictor is inflated by the other predictors. Generally, values around 5 or higher are considered to be problematic. We see here that the variance of the coefficient estimates for strength and mobility are increased by a factor of about 2.5 due to the relationship with the other predictors, mostly each other. Confidence intervals for our regression calculation are calculated using the square root, so the effect isn't quite as dramatic as what you see with the variance inflation factor. But it can mean the difference between significant and non-significant coefficients, especially in smaller samples. The condition index, which you see in the output to the right, is related to the eigenvalues of the data, or matrix. The condition index is the ratio between the largest eigenvalue and the individual eigenvalues. When predictors are closely related, the eigenvalues are smaller and the ratio gets larger. Values between 10 and 30 are thought to be problematic. Over 30, very much so. But you have to pay attention to how these values are calculated. More on that in a minute. The variance decomposition proportions tell you more about where the problem is. If the condition index is at least 10 and two decomposition proportions are higher than 0.80, there may be an issue. Here we see something close with mobility and strength, but the condition index is well below 10, so strictly speaking, according to the rules, we are okay. You have some choices here. When calculating the eigenvalues and the condition indices, you have a choice about whether to include the intercept and whether to standardize your predictors first. Not all packages, including Stata and R, standardized by default. In Stata, you have to add the core option to the colon command, and R, you have to use cond_index rather than the OLS collinearity diagnostic defaults. These will change your numbers, and there are arguments about which matrix to use. From what I've seen, the standardized approach is recommended. So the take-home message from this slide is that we don't see an obvious problem with collinearity, but it's worth looking further, and we know from initial screening that strength and mobility are pretty closely related, and in clinical practice, we would expect that. That makes sense. One way to explore what's going on by including two closely related variables, strength and mobility, is to look at marginal effects. So the two plots you see on your screen now compare the effect of mobility on admission on mobility at discharge with and without strength in the model. In these charts or models, the other predictors are constrained to their mean values, and sex is set to the default category, which is 0, male, and mobility admission is also centered like the other predictors. The line represents the predicted discharge mobility score across the range of admissions mobility scores, And again, these are centered, which is why you see the negative values. The shading is the standard error of the line and the standard error of prediction. Here you can see what strength does to the effect of mobility on admission in the model. Without strength, the slope changes substantially, and the standard error of both the coefficient for strength and the predicted mobility discharge score, according to mobility at admission, changes quite a bit. So adding strength causes a major shift in the slope of mobility at admission and increases the standard error slightly. That is confounding. So mobility at admission is confounded by lower extremity strength and vice versa. Each variable explains some of the effect of the other. And to me, this is clear evidence that both should be retained in the model. If you had added strength and the standard errors really exploded, but the slope didn't change so much, that would be a better case for collinearity, and it would have been clear in the diagnostics. Again, we venture into very dangerous territory for me, namely math, but this is a quick refresher that shows us why closely related variables can be a problem. Remember that your data is basically a matrix with a series of ones added to account for the intercept in the first column. And that matrix is transformed by the coefficient vector that you see in the middle of the screen, which then produces the vector of predicted values, which you see on the right. If you remember matrix multiplication, which I don't, you can see that indeed we can multiply our data by the coefficient vector to get a vector of predicted values. I just put these numbers in, so don't do the actual calculations, they won't come out. We solve for the vector of coefficients with the equation on the bottom on the left. And on the right, next to that, you're going to see now the equation for the variance of the coefficients. The fact that you have to invert x transpose x is where the problem comes in. Remember back in linear algebra when you had to put the original matrix on one side and then the identity matrix on the right side, and then you reduced it until the identity matrix was on the left side. I don't remember this, but you do. As the columns get closer and closer to one another, the harder it gets to invert them, and the larger the value for the variance of the coefficient becomes. This highlights why relationships between variables can be a problem in smaller data sets, even if the alarm bells for collinearity don't go off. Sometimes we just don't have enough power to handle the increase in standard errors. How much to allow is up to you, not the computer. So I think here we are pretty comfortable proceeding with both of those predictors in our model and realizing that one confounds the other and is therefore important to have both in, otherwise we might overestimate the effect of one. One thing we haven't discussed, however, is effect modification. It could be in this case that mobility at admission affects mobility at discharge differently, depending on the level of strength, rather than a simple case of confounding. I know that isn't the case here because I didn't set up the data that way, so I cheated a bit. But in a real data set, it's worth looking at a few plots and testing for interactions if, and I repeat, if you have an interaction that you can explain clinically. There are other videos available on effect modification and much smarter people available to explain that. So I encourage you to look at those resources if you think that might be an issue in your data set.